Okay, in this video we're going to go over Chapter 5, Proportional Reasoning. So I want you first to look at the student strategies on page 96 of your textbook and think about the three students' answers as we begin this chapter. So the unit. In order to discuss fraction problems, we need to know the unit, also referred to as the whole or the unit whole. Note, in dealing with fractions, the unit does not need to just be a single object. In whole numbers, 1 means one object, but in fraction, 1 means the whole amount you have before breaking occurs. So fractions are relative amounts. So if I have 8 cookies, so 1, 2, 3, 4, 5, 6, 7, 8 cookies, and I give away 3, what fraction remains? So what remains is going to be 5/8 of the whole. Okay, the pizza problem. If I order 3 pizzas and I cut each into 12ths, so I have 3 pizzas as my whole, and I'm dividing each of these into 12s. If a class of 12 students, in a class of 12 students, each was given 2 slices, so that means you had 12 and 12 more, or 12 times 2 is 24. So they have totally eaten these 2 pizzas. How much pizza was eaten by the class? So how much is what it says. It doesn't say how many slices. So how much of the whole? So in this situation, your answer is going to be 2/3 of it. Okay, because I have 2 pizzas totally gone, and I have 1 pizza remaining. So 2/3 was given out. Okay, units defined implicitly. If the unit is defined implicitly, you are given enough information to be able to work backwards and find out what the unit was. So an example would be if Rena had 4 candies left. So here Rena has 4 candies. And if these end up being 2/3 of some number she had before she started eating, what was her original number? Well, if you divide this in half, then this would be 1/3 and this would be 1/3. So then I know that to get the remaining, go back to the original, I have to add another 1/3. So I must have had 2, 4, 6 candies before I started. Okay, so that's how you would do that. You would work down to 1/3 and then triple that so that you had 3/3 again. So here would be 3/3, and that would be 6 candies. Okay, using units of various types. So key thing is mix this up. Don't make every problem a pizza problem. And the test book suggests that you can use, one continuous item like a pie, more than one continuous item, multiple pies, one or more continuous item that's perforated. So the example would be like a candy bar. Discrete items like the candies we just talked about. Discrete items organized in a specialized manner. That could be like, eggs in a carton or little candies in a candy box. Composite items use units consisting of single packages that have multiple objects inside. So like cupcakes in a little holder, 2 cupcakes in a little package. That would be a composite item with multiple items inside. Okay, reasoning up and down. When units are defined implicitly, like they were with the hard candies, which were discrete units, we have an excellent opportunity to use a process called reasoning up to the unit and then back down from the unit to another fraction. So look at this problem. The ladybugs on the left are equal to 3/4 of the ladybugs in my garden. So if this is 3/4, then I can say comfortably that this would be 1/4, okay, 1/4, 1/4, 1/4. So how many are in my garden? Well, I'm going to add another 1/4. So if I add 3 more ladybugs to the already 9 that's there, that is going to give me 12 ladybugs. So what I did was I reasoned down to 1/4 of the ladybugs ends up being 3 ladybugs. Therefore, 4/4 will be 3 times 4, or 12 ladybugs. Okay, units and unitizing. Unitizing refers to the process of constructing mental chunks in terms of which to think about a given quantity. If you want your class to think of a given quantity organized a certain way, you want to provide a detailed picture. Think of the example with a case of soda from the textbook. A case has 24 cans. You could have 4 6-packs or some other kind of combination. So if you want them to think about it in a certain way, then you want to be explicit about that. Okay, unitizing notation is a way to allow students to organize quantities in their own way. So they're going to identify for you what chunks they're using. So let's say, for example, I want two chunks, and each size of my chunk is, how about if it's 1 dozen eggs? So if I have 2 chunks, I would then have 2 dozen eggs, or 24 eggs. Flexibility in unitizing is important when trying to complete what is the best buy problems. Sometimes it's good to go down to the unit price, but sometimes you don't have to go all the way down to the unit price to really be able to answer your question. For example, in the textbook they said, well, if you know that 3 kiwis would cost you 67 cents, and you want to buy 9 kiwis, is there any reason why you'd have to go all the way down to the price of 1 kiwi and multiply by 9? That wouldn't be the most efficient way to do it. So you would just say 9 kiwis would be 3 times the 67 cents, and you would be done. So there's no need to always go down to a unit price. Okay, when thinking of best buy problems, allow the students to draw out their solutions and compare answers. Some may use unit pricing, but others may find more interesting ways to solve the problem, and the key is to be flexible and to allow for that discussion. Okay, classroom activities to encourage unitizing. Unitizing plays an important role in several of the processes needed to understand fractions, especially in sharing, partitioning, and figuring out what fractions are equivalent. Since children have a tendency to only think in terms of whole numbers, be sure to encourage non-traditional chunks that involve fractions. For example, going back to the case of cola, so if you know of the case of soda, so there's 24 cans generally in a case, but they now make those little half cans, so you can say 48 and my unit is the half can. Okay, so that's going to introduce the fraction of a half. So be flexible with that. Encourage the use of fractions because it will only help their thought process. Okay, unitizing, visualizing, and fraction equivalence. They all have a symbiotic relationship. This is very colorful patterns. On page 109 in our book, you can see the pattern that they use, and it's a very good way to visually stretch to think about how these different squares or rectangles are divided up and how we can speak about them. Okay, ratio tables is another nice way to demonstrate your reasoning. So I filled this one all out. So for example, if 3 pizzas serve 9 people, how many pizzas will I need to serve 108? So all the way down here, here is your goal. All right, so if you know this is what was given. So this is the given right here. So working with your given, you can double it, and that doubles both columns because they are proportionally related. So you're going to get to 6 to 18, and then double it again, 12 to 36. Double it again, and you can get to 72. Now, you can't get to 108 by doubling. However, you can add these 2 together and these 2 together so that you know that 36 pizzas, will feed 108 people. So you can use this table to reason to the point where you are able to solve the problem. Comparison problems are another nice thing to work on, and you can also use a table with that. So here it says 4 quantities forming 2 ratios are given. The task is to find whether the ratios are equivalent, or if not, which is greater or smaller. So which vehicle has the fastest average speed? Okay, a truck that travels 126 miles in 1.5 hours, or a car that travels 135 miles in 1 3/4 hours. So set up your table. So under my truck, I'm going to say 126 miles, and I'm going to say an hour and a half, but instead I'm going to say 3 halves. Okay, for the car, it's going 135 miles in 1 3/4 hours. So I want to figure out if I can get this down to a common time unit. And I'm thinking, because I'm thinking fourths are over here and halves are over here, I could probably get everything down to fourths and then do a direct comparison. So let's work at it on underneath the truck first. So if I divide 3 halves by 3, I get 1 half. If I divide 126 by 3, I get 42. Okay, so now go and divide 1 half by 2. That gives me 1/4 on partitioning. Divide 42 by 2, and that gives me 21. So I got down to 1/4. Let's get down to 1/4 on the other side. So the first thing I'm going to do, I'm going to change this hour to make it easier for me. I'm going to write it down as 7/4. Then I'm going to divide both sides by 7. That gives me 1/4 here, and this gives me 19 with a remainder of 2. I put that over 7. So now I can directly compare them, because look what's happening. This box gives me how many miles can that car travel in 1/4 of an hour, and this box gives me how many miles can the truck travel in the same amount of time. So there's my direct comparison, and when I compare the two, I find that the truck will go 21 miles. It will go further, and therefore it is traveling at a higher average rate of speed. Okay, missing value problems. Problems in which 3/4 are given and the 4th quarter is missing. So let's see. If it takes 4 people 3 days, so there's 1 given, 2 given. How long will it take 8 people? That's 3 out of the 4. I'm looking for this box right here. Now I have to think about this, because this is not a direct proportionality. This is an inverse proportionality. And that means as you increase the number of people that you have working, you decrease the number of days they have to work. Okay, so if you double the number of people, you will half the number of days. Okay, and that's how you would use the table to figure that out. Okay, ratio tables. The appropriate use of ratio table is to systematically organize one's work as the operations of multiplication, division, addition, and subtraction are combined to produce equivalent ratios until some target quantity is achieved. Okay, so let's look at the next page for that information. So the appropriate, I just said that. Okay, so an example of a horizontal ratio table. So here's a horizontal one. I have number of pizzas and number of people. So a party planning guide says that 3 pizzas will serve about 7 people. How much pizza, so how many pizza pies are needed for 350 people? Okay, so start out with your table, and you got to start thinking, logically. Okay, so if I have 3 and I have 7, I can multiply by 100, and That gives me 300 and 700. I need to get to 350, so then I'm going to divide by 2. Dividing by 2 gets me to 150. Okay, so let's think about this. 150, can't I... Well, I'm there. I guess I'm there. Let me reformat my thoughts here. Okay, so in this top horizontal one, here is your goal. Your goal is the 350. And I'm seeing that I overshot my target here and got to 700, but that was good because that's going to allow me to divide by 2 and come back to 350. So I get 150 for the number of pies I need. There's more than one way to skin a cat, so let's look at this next one. Here they reverse the people on the pizzas. So your goal is still to get to 35. What they did first is multiply the people by 5 and got to 35, and then multiply it by 10 and get to 350 that way. Either way, you know your reasoning is consistent because you're still getting 150 pies to feed 350 people. Okay, so useful strategies you want to consider. When you're doing these ratio tables, if you suggest your kids use multiplication and division by 2, 5, 10, and 100, that's going to make it easier for them. Like they can do other numbers if they want, but in terms of starting out, 2, 5, 10, and 100 are good ones to work with. It is very, very important to tell them to keep their exact answers, and that means if you get a fraction, keep your fraction. Don't round until the last step, otherwise you're going to have rounding error. If you begin with a fraction, multiplying by the number in the denominator will give you a whole number. So if I had 1/3 times 3 will give me a whole number. And sometimes you may go past the target quantity, and we did that here, and then divide, excuse me, or subtract to get back to it. Okay, use your multiples, multipliers, and divisors wisely. Okay, here we're going to increase the difficulty a little bit. If you try some problems that involve 3 quantities, and you're going to hold 2 things fixed, and then you're going to change 2 things and hold 1 fixed, you can look at page 116, and they give you a nice table that they demonstrate that in, using number of men, cords of wood, and time in hours. I'm going to do the cupcake one here for you. It's still only 2 quantities, but I wanted to put it in here because you have a column that tells you about your notes. So if you know that 15 cupcakes cost $3.36, find the cost of 38 cupcakes. So they kind of did something neat here. They multiplied by 2, and they're telling you what they're doing right here to get to 30. Now they cannot easily get to 38. At least they can't get there directly. So look what they did instead. They divided by 6 and got to 5, divided by... What did they do then? And then they moved it down, 30 divided by 10, so they came up here, and they divided by 10, and they got the 3. And now what they're going to do is they're going to add these columns to get your 38. So don't include the 15, but include the 30, the 5, and the 3, and you can figure out the cost of 38 cupcakes in that fashion. Okay, so notice, you're not going to round until you get here. So you would probably report it as 851. You're probably not going to include the thousand spot because it's a monetary value. Okay, so let's keep going. Okay, in analyzing relationships, scale factors is the factor that increases or decreases both quantities in a problem. Okay, so you have to know if you're doing proportional reasoning that the scale factor will make it go up, make both quantities go up, or make both quantities go down. They're not going to go opposite directions. You can include a scale factor in a function as well. So quantity B equals some constant times quantity A. And in this situation, that constant would be the scale factor. Okay, again, key. Both quantities are changing in the same direction. In inversely proportional problems, and that's where they change in opposite directions, you would have something like this, and notice that you are going to have a fraction like this, so that as one goes up, the other goes down. Okay, so your constant ends up being a numerator and your other variable ends up being a denominator, whereas when they're changing in the same direction, your constant was a coefficient to the other quantity. So just make sure you understand that. And that how the direction results from the problem is going to be individualized to the problem. So make sure you understand what they're telling you, and make sure that your students always think, now wait, is this inverse or is this directionally proportional? Okay, percents are simply fractions. Okay, they're decimal fractions. The denominator is always going to be 100. So you can represent that. Let's say, for example, 50 over 100 is equivalent to 50%. A lot of textbooks and a lot of curriculum introduced percents way later in this whole section with fractions, but you really can incorporate it because it's just a special kind of fraction, and the same rules will apply. Okay, percents as an instructional task. When children are encouraged to reason up and down throughout fraction instruction, reasoning with percent is easy and natural. So two best strategy. The first strategy is to make sense of the given statement and reason from given to unknown. Okay, you're reasoning from given to unknown. The second approach is to reason up or down after selecting some well-known benchmark. Okay, so you have a couple of ways to start this. Okay, reasoning with percent. So if you want to know 32 is what percent of 40, okay, 32 is going to be your numerator. 40 is going to be your denominator. Your goal is to get to 100 because you want percent. So if you know you have 32 over 40, doubling it gives you 64 over 80. Dividing by 10 gives you 8 over 10, and then multiplying by 10 gives you 80 over 100, which solves your problem. Okay, so now what I know is that 32 over 40 is equivalent to 80 over 100, which is also equivalent to 80%. Okay, so reading the next one carefully, 35% of what is 21? 21 is the numerator. Okay, this is the numerator, this is the denominator. This is what they gave you to work with. So you're at 35 numerator over 100 denominator. Divide by 5, you get to 7 over 20. Your goal is to get to 21 in the numerator. You can do that by multiplying by 3, and so then you know the number that is your denominator is your 60. So 35 over 100 is equivalent to 21 over 60. And there's one more over here. Okay, 30 is what percent of 80? So 30 is the numerator, 80 is the denominator. Numerator, denominator. Your goal is to get your percent, so therefore your goal is to get your denominator to 100. You can't get there directly, but look what they did. They divided by 2 twice and then multiplied by 5. And when they divided by 2 the second time, they got a fraction, which they presented as that fraction, and then they have a fraction in the final answer as well. Okay, so that concludes this chapter. So now look at the activities beginning on page 121. Work them through, check your answers and more, and then look at the problems in the problem set for this chapter.